Welcome to the deep dive. AI is already pretty amazing at spotting patterns, making predictions.
Yeah, definitely. It's got that pattern recognition down.
But what if we could push it further? Make AI that doesn't just react, but actually thinks its way through really complex stuff, more like how we humans tackle problems. That's what we're getting into today.
Exactly. And think about the big models everyone talks about, the LLMs. They're impressive, sure. Writing poems, answering questions.
Right.
But throw something really logically demanding at them or, something needing careful steps or data that's changing all the time. They can kind of wobble.
Yeah, and sometimes they just make things up
Mm.
confidently, those hallucinations.
Uh-huh. The dreaded hallucinations.
So yeah, we've been looking at some really interesting ideas about leveling up AI's whole reasoning game. It's centered around this idea called composable meta-reasoning components. Now, for our listeners, folks who want to really get this without drowning in jargon, think of it like this. We're talking about building AI that's not just smart, but smart about how it uses its smarts.
Yeah, that's a good way to put it. Our goal today really is to explore how AI can get much more adaptable, more efficient, and the inspiration comes from us, from human thinking.
How's that?
Well, we're pretty good usually at picking the right mental tool for whatever job we're facing, right? This deep dive is about how we can maybe give AI that same kind of cognitive flexibility.
Okay, and that leads us to, I think, two really core ideas we need to unpack. First up, meta-reasoning.
Meta reasoning. Sounds a bit meta.
Yeah, it does. But basically, it boils down to thinking about thinking.
Right.
So imagine an AI not just, say, solving a puzzle, but also sort of watching itself solve it, asking, is this approach actually working? And if not, being able to, switch strategies. That's meta-reasoning.
Precisely. It's the system actively monitoring its own internal processes, how it's using its compute power, what methods it's deploying, and crucially, adjusting those things on the fly.
Okay, that's one. The second big idea is composability.
Composability.
Okay, this one comes more from software engineering. Think of building with Legos. You have these standard blocks, and you can combine them in endless ways to build something complex. Composability in software is about building systems from small, independent, reusable parts. Makes things super flexible.
Right, because you can add new pieces, take some away, rearrange them without having to rebuild the whole thing from scratch.
Exactly. So put those two together, meta-reasoning and composability.
And you get composable meta-reasoning components?
Here it is. These are like those Lego bricks. But specifically for the AI's thinking about thinking job, each component is a distinct, reusable unit designed for one specific part of that meta-level control.
So you might have one component whose whole job is just monitoring progress towards a goal.
Yeah, or another one that evaluates if the current strategy is any good.
Or one that actually picks a new strategy if the current one's failing.
And maybe another for deciding how much processing power to use or realizing, hey, I need to learn something new here, or oops, made a mistake, need to fix that.
And what's really profound here, I think, is the shift in perspective for AI design. Well, we're moving away from designing one fixed way for an AI to reason. Instead, the focus shifts to designing a system that can intelligently figure out how to reason in the first place.
Ah, okay. So it's about giving the AI the ability to tailor its own problem-solving approach.
Exactly. Depending on the task, the context, what resources it has, and importantly, how well it's actually doing.
It's like instead of just having one chef who knows maybe 5 recipes, you have a system that can assemble a whole kitchen team specialists based on what's on the menu tonight and what ingredients are fresh.
That's a great analogy. So the core change is designing the orchestrator, not just the individual musicians, designing the system that manages the reasoners.
Okay, so this meta-reasoning concept,
Yeah.
where did that really bubble up from? Is it purely an AI thing?
Well, no, not purely. It has really strong roots both in AI itself and in cognitive science, how we understand human thought.
Right.
Essentially, it applies to any intelligent agent, human or machine, that can observe, evaluate, and then, adjust its own thinking processes.
And looking at our own minds must give some clues, right?
Oh, absolutely. Human metacognition, that's our term for our own thinking about thinking, is a huge source of inspiration.
Like what specifically?
Well, think about how we seem to have different modes of thought, sometimes quick and intuitive, other times slow and deliberate, more analytical.
Yeah, Kahneman's System 1 and System 2 thinking.
Exactly. Meta-reasoning or metacognition in us might be what helps us decide which system, which mode is best for a given situation. Plus, we have these internal signals, right? Like a feeling of knowing something, even if you can't recall it immediately, or that nagging feeling of error when something seems off.
Yeah, the little internal alarm bell.
Precisely. Those act as guides steering our cognitive processes. And in AI, the goal is similar but also practical. How does a system operate effectively with limited time, limited compute?
So it's not just about being correct, but being efficiently correct.
Yes, finding the best way to think to get the answer. And that means making a clear distinction. There's reasoning about the outside world, that's the object level, and then there's reasoning about its own reasoning, that's the meta level.
Okay, so what are the main jobs this meta-reasoning actually does? What are its key functions?
You can break it down into a few core functions. First, monitoring, just keeping tabs on how the current reasoning is progressing.
Like, how confident am I in this intermediate step? Did I just make a mistake?
Exactly. Second is control or regulation, using that monitoring info to make decisions. How much effort should I keep pouring into this? Should I switch strategies? Is it time to stop?
Makes sense. If you realize you're digging in the wrong place, you need to be able to stop digging and look elsewhere.
Precisely. Which brings us to the third function, strategy selection and discovery. Choosing the best known method, but also potentially figuring out totally new ways to approach a problem it hasn't seen before.
And the fourth.
Resource allocation. This is crucial. Intelligently deciding how to spend limited resources, processor cycles, time to get the best result possible. It's like the AI asking itself, is spending another microsecond really likely to improve my answer significantly, or should I just go with what I have?
Making those smart trade-offs with its mental energy.
Exactly. Cognitive economy, you could call it.
So AI researchers have actually formalized this, put some math behind thinking about thinking.
Oh, yes. Definitely within AI. You see concepts like meta-level rationality, basically. How well does an AI balance the potential payoff of doing some computation versus the cost of doing it?
Okay.
Then there's bounded optimality, which is maybe more realistic, acknowledging that even the meta-reasoning process itself isn't perfect and has limits.
Right. Thinking about thinking also takes effort.
It does. There's value of computation, VOC, which tries to quantify, often probabilistically, whether doing a specific computation is actually worth it. And meta-level Markov decision processes, or meta-MDPs, model strategy selection as a sequence of choices, which then lets the AI learn better meta-reasoning strategies using techniques like reinforcement learning.
Okay, wow, so that covers the meta-reasoning part in some depth.
Yeah.
Now let's circle back to composability. You said it's originally a software idea.
That's right, primarily from software engineering. It's a design philosophy focused on how system components interact. The whole point is to build complex things by assembling smaller, independent units, like those Legos again.
Making it easy to mix and match.
Exactly, leading to highly flexible and maintainable designs.
So what makes a software design truly composable? What are the key ingredients?
There are several core principles. Modularity is fundamental. Each piece is self-contained, does its own thing.
Okay.
Autonomy, they operate independently. They talk to each other through well-defined interfaces like contracts that hide how messy the insides might be.
So you don't need to know how the block works, just what it does and how to connect to it.
Precisely. Loose coupling is vital. You want to minimize how much components depend on each other. Change one, and hopefully you don't break 10 others.
That sounds ideal.
It is. Ideally, components are also stateless, meaning each request is handled fresh without relying on past interactions, though that's not always possible or desirable, especially in reasoning.
Right.
And then you have things like standardization, common ways of communicating, and concepts like separation of concerns and abstraction that help keep things organized.
Sounds like a recipe for much saner software development. What are the payoffs in practice?
Oh, the benefits are huge. Reusability is obvious. Build a component once, use it in many places, saves tons of time and effort.
Definitely.
Scalability gets easier because you can often scale up just the parts that are bottlenecks, not the whole system. Flexibility and adaptability, you can reconfigure things, swap components, add new features more easily.
Makes maintenance less of a headache, too, I bet.
Much less. You're dealing with smaller, contained units. It also speeds up development, simplifies testing, improves interoperability between different systems. Ultimately, it leads to systems that are more cost-effective and easier to future-proof.
Okay, so how does this software idea translate to AI? Yeah. And maybe even to how our own minds work?
Well, while it started in software, the core ideas are becoming super relevant for AI and cognitive modeling. For AI builders, it's a way to tame complexity, right?
Yeah.
Simplifying how different AI capabilities connect and interact. In cognitive science, it helps formalize theories about how different mental faculties might combine. How does language interact with planning, for instance? But maybe the biggest win for AI is tackling real-world complexity. Composability lets an AI dynamically combine different learned models or reasoning skills as needed.
So it can build a custom solution on the fly.
Kind of, yeah. It even echoes some theories about how our complex thoughts might emerge from combining simpler concepts. Plus, frankly, modular AI systems can be easier for us humans to understand and therefore to trust.
But it can't be a perfect one-to-one mapping, right? Applying software principles to AI reasoning must have some wrinkles.
Definitely nuances, yes.
Yeah.
The goals overlap managing complexity, enabling reuse, but AI often aims higher than just software efficiency. We're trying to mimic human flexibility or achieve totally new, intelligent behaviors.
And what about that stateless ideal you mentioned?
Right, that's a key difference. The software ideal of stateless components often clashes with AI reasoning. Things like memory, holding beliefs, tracking steps in an argument, these are inherently stateful.
You need to remember what happened before.
Exactly. So, composable meta-reasoning components in AI might need quite sophisticated ways to manage their internal state, which adds another layer of complexity compared to some simpler software components.
Okay, got it. So how do we actually combine these two big ideas, meta-reasoning and composability, in an AI system? What does that look like?
The core idea is applying those composability principles, modularity, clear interfaces, reusability directly to the meta-reasoning process itself.
So instead of one big control center doing all the meta thinking.
Right, you break it down. You envision meta-reasoning as a collection of distinct, specialized components that work together.
So it's not just one AI brain. It's like a committee of specialized mini-brains helping the main reasoning process manage itself.
That's a fantastic analogy, yes. Each specialized component handles a specific aspect of that meta-level control. Like one monitors performance, another assesses certainty, another detects errors, another selects strategies, another manages resources, maybe another triggers learning when needed.
And the composable part means you can mix and match these mini-brains, use different combinations for different situations.
Exactly that. Composability enables that flexible combination. So for a simple problem, maybe you only need a basic monitor and a default strategy selector.
Keep it simple.
But for a really gnarly, complex challenge, the system could dynamically pull in more sophisticated components. Maybe a detailed process tracer, an evaluator that simulates different strategies before choosing, a meta-level planner to optimize the use of thinking time.
So the system adapts its own management structure based on the difficulty.
Precisely. It's about building systems that don't just reason, but have an adaptable way of managing that reasoning.
This sounds like it really pulls together ideas from lots of different research areas.
It absolutely does. It stands on the shoulders of foundational AI work on rational agents, decision theory, but also pulls heavily from cognitive science, like we discussed, on human metacognition and cognitive architectures.
And the recent LLM boom must be a factor.
Huge factor. The obvious reasoning limitations of current LLMs have really spurred interest in improving them, and meta-reasoning offers a path. Plus, fields like robotics, where you need constant adaptation to the physical world, and multi-agent systems dealing with coordinating multiple thinkers are highly relevant.
Even more theoretical stuff.
Yep, computational logic, metaprogramming. These provide formal tools for actually reasoning about computation itself, which is fundamental here.
It almost sounds like different research communities might have been working on parallel tracks, hitting similar problems, but maybe using different names for things.
That is a really sharp observation, and it's a known issue sometimes called the heterogeneity problem.
Okay.
Researchers in, say, NLP working on LLMs might talk about prompt engineering to guide reasoning, while robotics folks talk about execution monitoring, and multi-agent people talk about coordination mechanisms. But underneath, they're often grappling with related meta-level control issues.
So we kind of need a common language, a shared framework to connect these dots.
Precisely. And there's a growing realization that the strategies humans evolved for metacognition might be incredibly valuable blueprints. We're seeing more research explicitly trying to map cognitive science models onto formal AI approaches, trying to bridge that gap.
This whole idea of AI thinking about its own thinking, it's not brand new though, right? It has a history.
Oh, definitely not new. It has a rich history in AI. Early work explored meta-level control for managing program execution. Russell and Weffeld's work in the late 80s on rational meta-reasoning and the value of computation concept was really seminal in formalizing when an AI should bother thinking more.
Right, making the cost-benefit analysis explicit.
Exactly. And like we said, cognitive science has been probing human metacognition in parallel for decades.
And fast forwarding to today, with the LLM revolution, how is this meta-reasoning idea being applied there? Because that's where a lot of the buzz is.
Yeah, the limitations of LLMs on complex reasoning tasks have been a major catalyst. We're seeing techniques like meta-reasoning prompting or MRP.
Okay, what's that?
It's where the prompt itself guides the LLM to explicitly choose the best reasoning strategy for the task at hand from a set of options also described in the prompt.
So the prompt tells it how to think about the problem, not just what the problem is.
Exactly. There are also proposals for Bayesian meta-reasoning frameworks for LLMs, aiming to give them distinct, identifiable modules for things like self-awareness, monitoring, evaluation, drawing directly from human metacognition models.
Interesting.
Then you have things like metacot, meta-chain of thought, and multi-chain reasoning, MCR, which try to make the step-by-step reasoning of LLMs more structured, more explicit, and ultimately more reliable.
Trying to avoid those leaps of faith or hallucinations.
Right. And research into reflective sisters or introspection explores how an AI might examine its own internal states and trace back errors to improve itself. Even formal logic approaches, like using meta-interpreters, are being explored for more rigorous control.
It's fascinating how these abstract concepts are getting built into actual AI architectures.
Absolutely. And we're seeing some common architectural patterns emerge for implementing this composable meta-reasoning. A classic one is hierarchical architectures.
Meaning?
You have a clear meta-level controller that oversees and directs the object-level reasoning processes. And crucially, that meta-level itself can be composed of different specialized components.
So the manager overseeing the workers, but the manager's job is also broken down and handled by a team of specialists.
Exactly that. Another pattern is pipeline architectures, common in areas like, say, computer vision. Here, meta-reasoning components might dynamically tune the parameters or even swap out modules within the processing pipeline based on the input or intermediate results.
Adjusting the assembly line on the fly.
Kind of, yeah. Then you see modular reasoning frameworks. Think of systems like MRKL, where there's a central router basically acting as a meta-reasoner that decides which specialized expert module is best suited to handle an incoming query.
Directing traffic to the right specialist.
Precisely. And finally, many agent architectures, especially in robotics and planning, explicitly include modules for things like monitoring actions, detecting failures, and triggering repair or replanning mechanisms. These are all forms of meta-level control.
It really seems the common thread is breaking down the big reasoning challenge into smaller, more manageable and controllable pieces.
That's the key insight. And these patterns aren't mutually exclusive. You often see hybrids combining elements from several approaches depending on the specific needs of the application.
Could you give us a few concrete examples? How are these composable meta-reasoning bits being used in specific AI systems or frameworks people might have heard of?
Sure. Let's stick with LLMs for a moment. Meta-reasoning prompting, MRP, like we mentioned. The LLM itself acts as the meta-reasoner. It looks at the problem, then picks a reasoning method described in the prompt, maybe step-by-step thinking, maybe generating multiple options that it thinks fits best. It's composing strategies via the prompt structure.
Okay, so the composability is sort of implicit in the prompt design and the LLM's choice.
Exactly. Then there's active research on those Bayesian meta-reasoning frameworks for LLMs. The vision there is explicit modules for self-awareness, monitoring, evaluation, memory management, really trying to mirror human metacognitive functions.
More structured.
Yes. Metacode aims to make the LLM learn more structured, latent reasoning steps internally. And multi-chain reasoning, MCR, is interesting. It often uses a separate LLM. One LLM generates multiple possible reasoning chains, some potentially flawed.
Right.
And then a second meta LLM acts like a critic, analyzing all those chains, extracting the good parts, and synthesizing a final, more reliable answer.
Like peer review for AI reasoning.
Sort of. Even meta prompting itself is relevant, focusing on abstracting prompt structures to get better performance and generalization, sometimes even having the LLM design new prompts recursively.
Wow, that's a lot just within LLMs. What about outside that? Robotics, planning?
Yeah, absolutely. In robotics, dealing with unpredictable environments, you have frameworks like HYDRA. It's explicitly designed with components for detecting novelty. Hey, that wasn't there before. assessing its importance, and then repairing the robot's internal world model to account for the change.
So it can update its map for understanding.
Exactly. And related to that are various architectures for robotics failure detection and repair. These integrate planning with continuous monitoring. Is this action working as expected? Diagnosing failures if they occur, and selecting repair strategies, maybe drawing on a memory of past similar failures.
So the robot isn't just executing blindly, it's checking reality against its plan and can fix things.
Precisely. There are other cool examples too. Meta AQUA was an older story understanding system, but it was notable for its ability to introspect on why it failed to understand something, learn from that failure, and improve.
Learning from mistakes, a very meta skill.
Indeed. Or work on meta-reasoning for modular systems, using reinforcement learning to dynamically configure software pipelines, like optimizing a complex computer vision system. Even meta-interpreters and logic programming programs that reason about other programs fit this broader theme.
It's definitely becoming clear that mixing different reasoning styles, different knowledge representations.
Yeah.
That's a common thread here.
Yes, and composability is often what makes those hybrid approaches work cleanly, with the meta-reasoning layer acting as the intelligent glue or conductor. This idea of a reasoning pool, or a toolbox of expert modules managed by a higher-level controller, keeps popping up. It really mirrors how we seem to have a mental toolkit of heuristics and strategies.
Can we walk through maybe one or two super simple examples just to see how these components might interact?
Sure, let's try. Imagine an LLM using meta-reasoning prompting for a tricky math problem. Step 1. The meta-reasoner part, prompt-guided, analyzes the problem type. Step 2. It looks at its available strategies, maybe defined in the prompt, perhaps step-by-step derivation, or tree of thoughts exploration. Step 3. It selects tree of thoughts as most promising for exploring different solution paths. Step 4. It then applies that specific reasoning method.
Okay, selection then execution. What about the robot example with HYDRA?
Right. Robots moving expects clear path. Sensor detects an unexpected box. Step 1. A plan inconsistency monitor component flags the mismatch. Sensor data doesn't match map. Step 2. A novelty determination component confirms, yep, that's a new object, not just sensor noise. Step 3. A model repair component kicks in to update the robot's internal map with the box's location. Step 4. The planner then uses the updated map to find a new route around the box.
Got it. Each component does its specific job, passing information along to handle something unexpected.
Exactly. One more quick one. Multi-chain reasoning. Ask a complex question. Base LLM generates, say, 3 different lines of reasoning chains. Some might be good, some flawed. A separate meta-reasoner LLM then looks at all 3 chains, identifies the valid steps or correct pieces of info, even from the flawed chains, and synthesizes a single, better, combined answer, maybe explaining its synthesis.
Ah, like a manager reviewing drafts from 3 team members, pulling the best sentences from each to create the final report.
Precisely that kind of idea, and that ability to compose these different meta-level functions, selection, monitoring, repair, synthesis. That's what gives these systems their power to adapt, handle novelty, and be more reliable.
This all sounds incredibly powerful. What are the headline advantages we expect from pushing AI in this composable meta-reasoning direction?
Well, I think one of the absolute biggest is massively enhanced flexibility and adaptability. The specific task. Simple tools for simple jobs, heavy machinery for complex ones. It mimics that cognitive flexibility we admire in humans.
Right.
And it makes the AI better at adapting to new information or changing circumstances. Because it's modular, you can update or add specific reasoning skills without a total overhaul.
So it's not just smart in one way, it can change how it's smart when the world changes.
Exactly. Another huge advantage is efficiency, scalability, and resource management.
The not wasting effort part.
Precisely. By thinking about its own thinking, the AI can avoid dead-end computations, allocate its processing power and time more intelligently. It can make those calculated trade-offs. Is more thinking likely to pay off here, or should I move on?
Makes total sense. Don't spin your wheels unnecessarily.
And finally, this approach promises improved robustness, generalization, and maintainability.
How does that work?
Having dedicated monitoring and error detection components makes the system more resilient when things go wrong. Being adaptable inherently helps it generalize better to new, unseen problems. And from just a practical engineering view, modular systems are simply easier to understand, debug, update, and maintain over time.
It really does sound like this could tackle some of the core weaknesses we see in AI today.
That's the hope and the goal. By building AI that can effectively reason about its own reasoning, we can potentially create AI systems that are significantly more intelligent, far more adaptable, and ultimately much more reliable.
Okay, so wrapping this up, we've done a pretty deep dive today into this idea of composable meta-reasoning. It really feels like a key path forward for making AI more flexible, efficient, and robust.
Yeah, the core takeaway is enabling AI to intelligently manage its own thought processes using these modular, reusable components.
Which lets it tailor its approach based on the task, the context, the resources, and critically, feedback on its own performance.
Exactly. It's a fundamental shift, really, moving from designing a reasoner to designing a system that orchestrates reasoning itself.
That is a powerful concept. And for everyone listening, as you grapple with complexity in your own work or life, trying to sort through information overload, maybe consider this. How could breaking down your own complex tasks into smaller steps that involve self-monitoring, evaluating your approach, and adjusting as you go, how might that apply to your own learning and problem solving? Definitely some food for thought there. Thanks for joining us on this deep dive.